Every single breath you take is dominated by a mysterious, invisible gas that does absolutely nothing to your body, and yet, without it, every ocean would boil or freeze, every forest would ignite, and human civilization would never have existed. That gas is nitrogen. Right now, the air surrounding you is roughly 78.09% nitrogen, about 20.95% oxygen, 0.93% argon, and a scattering of trace gases including carbon dioxide at a mere 0.04%. Most people assume oxygen is the star of the atmosphere, the dominant force keeping us alive, the gas that matters most. But oxygen is a minority player, holding barely 1/5 of the atmospheric stage. The true ruler of the sky, the molecule that outnumbers every other gas nearly 4-1, is molecular nitrogen, N2, a colorless, odorless, tasteless substance that slips in and out of your lungs with every breath and never reacts with a single cell in your body. It enters, it leaves, it does nothing. And yet this supremely passive, seemingly pointless gas is the single most important structural component of the atmosphere that makes life on Earth possible. The question is, how did such an unreactive, forgettable molecule come to dominate the air of an entire planet? The answer stretches from the first seconds after the Big Bang through the thermonuclear furnaces of dying stars, across the hellish infancy of a molten Earth, through billions of years of microbial chemistry and planetary evolution, and forward into the challenges that will determine whether human civilization can survive beyond this one small world. The story of nitrogen is the story of everything. To understand why nitrogen dominates the atmosphere of Earth, you first have to understand where nitrogen comes from, and in the grand scheme of the universe. Nitrogen is not particularly abundant. After the Big Bang, roughly 13.8 billion years ago, the cosmos was flooded almost exclusively with hydrogen and helium. These two elements were forged in the first few minutes of the universe's existence, and they still account for about 98% of all ordinary matter. By mass, hydrogen makes up approximately 75% of the observable universe, and helium about 23%. Everything else, every atom of carbon, oxygen, iron, gold, and nitrogen, was produced later, inside stars, through the process of stellar nucleosynthesis. When you examine the cosmic abundance of elements by mass, oxygen comes in at roughly 1%, carbon at about 0.5%, neon at around 0.13%, and nitrogen sits at approximately 0.1%. In the grand cosmic census, nitrogen is a minor player, far less abundant than hydrogen, helium, oxygen, or carbon. It is not rare in the way that gold or platinum is rare, but it is certainly not one of the universe's headline elements. So the first puzzle is immediate and striking. A gas that constitutes less than 0.1% of the universe's mass somehow ended up commanding 78% of the atmosphere of this particular rocky planet. That discrepancy demands an explanation, and the explanation begins inside stars. Nitrogen is produced in stars primarily through what is known as the CNO cycle, the carbon-nitrogen-oxygen cycle, which is one of the two main sets of fusion reactions by which stars convert hydrogen into helium. In stars roughly 1.3 times the mass of our Sun, or larger, the CNO cycle becomes the dominant hydrogen-burning mechanism. In this process, carbon-12 atoms act as catalysts, and nitrogen-14 is produced as an intermediate product. However, the CNO cycle does not generate nitrogen in enormous quantities relative to other elements. Carbon and oxygen, by contrast, are produced copiously in the helium-burning phases of massive stars and are then scattered across space when those stars explode as supernovae. The result is that the interstellar medium, the raw material from which new solar systems form, is relatively enriched in oxygen and carbon, but less so in nitrogen. For nitrogen to accumulate in significant quantities in the interstellar medium, you need multiple generations of stars that have already produced carbon and oxygen, because the CNO cycle requires pre-existing carbon to function. This means nitrogen production ramped up more slowly in the early universe than the production of oxygen or carbon. By the time our solar system, formed about 4.6 billion years ago from a collapsing cloud of gas and dust, nitrogen was present in that cloud, but it was not the dominant heavy element. It existed primarily in molecular forms such as ammonia, or locked into organic compounds within icy grains and planetesimals. The Sun itself reflects this cosmic composition. Spectroscopic analysis of the solar atmosphere shows that oxygen is more abundant than carbon, and carbon is more abundant than nitrogen, following the expected hierarchy of stellar nucleosynthesis products. When you survey the planets and moons of our solar system, the rarity of nitrogen-dominated atmospheres becomes strikingly clear. The gas giants, Jupiter and Saturn, have atmospheres overwhelmingly composed of hydrogen and helium, mirroring the primordial composition of the solar nebula. The ice giants, Uranus and Neptune, also have hydrogen-helium envelopes with traces of methane. Among the rocky planets, Venus has a crushingly dense atmosphere that is 96.5% carbon dioxide and about 3.5% nitrogen, with a surface pressure more than 90 times that of Earth. Mars has a thin, wispy atmosphere that is about 95.3% carbon dioxide and only 2.7% nitrogen, with a surface pressure of just 0.006 atmospheres, less than 1% of Earth's. Mercury has virtually no atmosphere at all. In this planetary lineup, Earth stands out as a radical anomaly. It is the only rocky planet where nitrogen is the dominant atmospheric gas. There is only one other body in the solar system that shares this distinction, and it is not a planet but a moon. Saturn's largest moon, Titan, possesses a thick, hazy atmosphere that is approximately 95 to 98% nitrogen, with most of the remainder being methane and trace hydrocarbons. Titan's atmosphere is actually denser than Earth's, with a surface pressure about 1.45 times that of our planet, which is remarkable given that Titan is much smaller than Earth and has a surface gravity only about 1/7 of ours. The leading hypothesis for Titan's nitrogen atmosphere involves the photochemical decomposition of ammonia. Ammonia ice, present in Titan's original composition, was broken apart by ultraviolet radiation from the Sun over billions of years, releasing nitrogen gas that accumulated in the atmosphere while hydrogen, being light, escaped into space. But Titan remains a frigid, alien world, with surface temperatures around -179 degrees Celsius, and its nitrogen atmosphere plays a fundamentally different role than it does on Earth. The bottom line is that in our entire solar system, only Earth and Titan have nitrogen-dominated atmospheres, and among planets, Earth is unique. This raises the central question with even greater urgency. What happened on Earth that did not happen on Venus, Mars, or anywhere else to allow nitrogen to become the atmospheric sovereign? The answer begins with the hellish conditions of Earth's earliest history. When Earth first coalesced from the solar nebula roughly 4.54 billion years ago, it was a world of unimaginable violence. The young planet was continuously bombarded by asteroids and comets, a period known as the Late Heavy Bombardment that may have continued until about 3.8 billion years ago. The energy from these impacts, combined with the heat from radioactive decay and gravitational compression, kept Earth's surface molten or semi-molten for hundreds of millions of years. The earliest atmosphere, sometimes called the primary atmosphere, was likely composed of gases captured from the solar nebula, mostly hydrogen and helium, but this light envelope was quickly stripped away by the intense solar wind from the young sun and by the enormous energy of impacts. What replaced it was a secondary atmosphere, degassed from the planet's interior through volcanic eruptions and outgassing. This secondary atmosphere bore no resemblance to the air we breathe today. Based on analyses of ancient rocks, studies of volcanic emissions, and comparisons with other planets, scientists believe the early atmosphere was dominated by carbon dioxide, with significant amounts of water vapor and lesser quantities of nitrogen, sulfur dioxide, hydrogen sulfide, methane, ammonia, and other volcanic gases. Some researchers have compared the early Earth's atmosphere to what we see on Venus today, an atmosphere crushed under massive quantities of CO2, with nitrogen present but as a secondary component. The atmospheric pressure at the surface may have been tens or even hundreds of times greater than today, owing to the enormous quantity of CO2. Temperatures were extreme. Free oxygen was essentially absent. If a modern human could somehow be transported to the surface of the early Earth, They would be dead within seconds from the heat, the toxic gases, and the utter lack of breathable air. This was, in every meaningful sense, a planet from hell. The transformation of this hellish atmosphere into the nitrogen-dominated, oxygen-containing atmosphere we know today was a process that unfolded over billions of years, driven by three great forces: water, geology, and life. The first crucial step was the formation of the oceans. As Earth gradually cooled, the vast quantities of water vapor in the atmosphere began to condense. Torrential rains, lasting perhaps millions of years, fell upon the young planet, gradually filling the basins that would become oceans. This was arguably the most important weather event in the history of the planet, because the formation of liquid water on the surface set in motion a cascade of chemical processes that would fundamentally alter the atmosphere. Carbon dioxide is moderately soluble in water. As the oceans formed, atmospheric CO2 began dissolving into seawater, forming carbonic acid. This carbonic acid reacted with dissolved minerals, particularly calcium and magnesium, to form carbonate minerals such as calcium carbonate. Over millions and eventually billions of years, these carbonates precipitated out of solution and accumulated on the ocean floor as limestone and other sedimentary rocks. This process, sometimes called the carbonate-silicate cycle, effectively locked away staggering quantities of carbon dioxide in solid rock, removing it from the atmosphere on a geological timescale. It is worth emphasizing the scale of this carbon sequestration. The total amount of carbon locked in Earth's limestone and other carbonate rocks is estimated to be equivalent to roughly 170,000 times the amount of CO2 currently in the atmosphere. If all of that carbon were released back into the atmosphere as CO2, Earth's surface pressure and temperature would be comparable to those of Venus. In other words, Earth has roughly the same inventory of carbon as Venus, but on Earth, most of it is safely stored in rocks rather than baking the atmosphere. While the oceans were chemically scrubbing CO2 from the atmosphere, the second great force, life, entered the scene. The exact timing and mechanism of the origin of life remain among the most profound unsolved questions in science. But the earliest evidence of life on Earth dates back to at least 3.7 billion years ago, and some contested evidence pushes this back to 4.1 billion years ago. The earliest organisms were simple, single-celled prokaryotes living in the oceans, likely deriving energy from chemical reactions rather than sunlight. But at some point, a revolutionary innovation emerged: oxygenic photosynthesis. The ability to use sunlight to split water molecules and release oxygen gas as a waste product while fixing carbon dioxide into organic molecules. This innovation is attributed to cyanobacteria, sometimes poetically called blue-green algae, and it would change the planet forever. Cyanobacteria began pumping oxygen into the oceans and, eventually, into the atmosphere. However, for a long time, the oxygen they produced was immediately consumed by chemical reactions. It oxidized dissolved iron in the oceans, creating the massive banded iron formations that we find in ancient rocks around the world, and it reacted with other reduced minerals and gases. It was only after these chemical sinks were largely saturated that free oxygen began to accumulate in the atmosphere in significant quantities. This tipping point, known as the Great Oxidation Event, occurred approximately 2.4 to 2.1 billion years ago. Atmospheric oxygen rose from essentially zero to perhaps a few percent, transforming the chemistry of the Earth's surface and atmosphere. For many of the anaerobic organisms that had dominated the planet until then, this was a catastrophe. Oxygen was toxic to them, and the Great Oxidation Event may have triggered one of the most severe mass extinctions in Earth's history, sometimes called the oxygen catastrophe. But for the lineage of organisms that would eventually give rise to complex multicellular life, including us, it was the defining moment. As oceans dissolved and locked away CO2, and as life consumed CO2 through photosynthesis and released oxygen, the atmosphere was progressively stripped of its original dominant components. Water vapor condensed into oceans. Carbon dioxide was buried in rocks and consumed by organisms. Sulfur-containing gases reacted with oxygen and were removed as sulfate minerals. Methane was oxidized. Hydrogen and helium, being the lightest gases, had long since escaped Earth's gravitational pull and drifted off into space. One by one, the original atmospheric gases were either chemically transformed, dissolved, locked into solid form, or lost to space. And through all of this subtraction, one gas remained essentially untouched: nitrogen. Nitrogen gas, N2, had been present in the atmosphere since the earliest days of Earth's secondary atmosphere, released through volcanic outgassing. But unlike CO2, nitrogen does not readily dissolve in water in large quantities. Unlike water vapor, it does not condense into liquid at Earth's surface temperatures. Unlike methane or sulfur gases, it does not readily react with oxygen under normal conditions. Unlike hydrogen or helium, it is heavy enough, with a molecular mass of 28 atomic mass units, to be firmly held by Earth's gravity. Nitrogen simply persisted. It did not leave, it did not dissolve, it did not react, it did not condense. It just stayed. And as everything else was removed around it, its relative concentration in the atmosphere climbed higher and higher. From a minor component of a CO2-dominated early atmosphere to the overwhelming majority of the atmosphere we have today. This is the essential mechanism by which nitrogen came to dominate. Not through any process that actively concentrated it, but through the removal of everything else. Nitrogen won the atmospheric throne not by conquest, but by default. The chemical basis for nitrogen's extraordinary persistence is rooted in the nature of the nitrogen-nitrogen triple bond. Each molecule of N2 consists of two nitrogen atoms joined by one of the strongest bonds in all of chemistry. A triple covalent bond with a bond dissociation energy of approximately 945 kilojoules per mole. To put this in perspective, the double bond in molecular oxygen, O2, has a bond energy of about 498 kilojoules per mole, and the carbon-carbon single bond in organic molecules is around 346 kilojoules per mole. The nitrogen triple bond is nearly twice as strong as the oxygen double bond and nearly 3 times as strong as a typical carbon-carbon bond. This extraordinary bond strength means that breaking apart an N2 molecule requires an enormous input of energy. At the temperatures and pressures found at Earth's surface, N2 is almost completely inert. It does not burn, it does not react with water, it does not corrode metals. It does not react with oxygen under normal conditions, and it does not interact with biological tissues. When you inhale air, the nitrogen molecules enter your lungs, bounce around inertly, and are exhaled unchanged. Your body cannot use them, cannot break them apart, cannot do anything with them. They are, from the perspective of your respiratory system, invisible passengers. This inertness is precisely why nitrogen survived while other gases did not. Carbon dioxide could be dissolved and locked away because it reacts readily with water and minerals. Oxygen could be consumed by oxidation reactions with iron, sulfur, and organic matter. Methane could be destroyed by oxidation. But nitrogen resisted all of these processes. It was, in a profound chemical sense, too stable to be removed. The very property that makes nitrogen seem useless, its refusal to participate in chemical reactions, is the property that allowed it to outlast every other gas in the atmosphere. This is the great paradox of nitrogen. It became the king of the atmosphere precisely because it was too inert to be anything else. It won by doing nothing, by being supremely, obstinately, magnificently unreactive. The comparison with Venus and Mars illuminates just how specific the conditions had to be for nitrogen to achieve atmospheric dominance. Venus is almost exactly the same size as Earth, with 95% of Earth's diameter and 82% of Earth's mass. It almost certainly started with a similar inventory of volatiles, including nitrogen, carbon dioxide, and water. But Venus is about 30% closer to the Sun than Earth. And this seemingly modest difference in orbital distance had catastrophic consequences. Venus may have had liquid water on its surface early in its history. Some climate models suggest oceans could have persisted for as long as 2 billion years. But eventually, the increasing luminosity of the Sun pushed Venus past a critical threshold. Water vapor accumulated in the upper atmosphere, where ultraviolet radiation split it into hydrogen and oxygen. The hydrogen escaped to space, and the oxygen reacted with surface minerals or was lost through other mechanisms. Without liquid water, Venus lost its ability to dissolve and sequester CO2. The carbon dioxide accumulated, driving temperatures higher in a runaway greenhouse effect, which drove more CO2 out of rocks and into the atmosphere, which drove temperatures higher still. Today, Venus's atmosphere is a stifling 96.5% CO2 with a surface temperature of about 465 degrees Celsius, hot enough to melt lead, and a pressure of 92 atmospheres. Venus does have nitrogen in its atmosphere, about 3.5% by volume, which in absolute terms is actually about 4 times the total mass of nitrogen in Earth's atmosphere, because Venus's atmosphere is so much more massive overall. But nitrogen is completely overwhelmed by the dominant CO2. On Venus, CO2 was never removed, so nitrogen never got the chance to be the majority gas. Mars tells the opposite cautionary tale. Mars is much smaller than Earth, with only about 11% of Earth's mass and 38% of its surface gravity. This weak gravity meant that Mars struggled to hold onto its atmosphere over geological time. Mars did have a thicker atmosphere early in its history. There is abundant evidence of ancient rivers, lakes, and possibly even an ocean on Mars, but without a strong global magnetic field to deflect the solar wind. Mars's atmosphere was gradually stripped away over billions of years by a process called sputtering. Today, Mars's atmosphere is vanishingly thin, with a surface pressure of about 600 pascals, less than 1% of Earth's sea level pressure. What remains is 95.3% CO2 and just 2.7% nitrogen. Mars had nitrogen too, but it lost most of its atmosphere entirely. And what little remains is still dominated by CO2, because there were never large, stable oceans to dissolve and bury the carbon dioxide. Earth sits in a remarkably fortunate middle ground, large enough to retain a substantial atmosphere, close enough to the sun for liquid water, but not so close as to trigger a runaway greenhouse, and blessed with the emergence of life that could actively draw down CO2 through photosynthesis. These 3 conditions, adequate gravity, liquid water, and biology, conspired over billions of years to strip away the original CO2-dominated atmosphere and leave nitrogen standing alone at the top. But nitrogen's dominance is far more than a chemical accident or a story of passive survival. Nitrogen plays a set of absolutely critical roles in maintaining the habitability of Earth. And if it were suddenly removed, the consequences would be catastrophic on a planetary scale. The most fundamental of these roles is the maintenance of atmospheric pressure. Earth's surface atmospheric pressure averages about 101.3 kilopascals, or about 14.7 pounds per square inch. Because nitrogen constitutes 78% of the atmosphere, it is responsible for roughly 78% of this pressure. Atmospheric pressure is not merely an abstract physical quantity. It directly determines whether water can exist as a liquid on the planet's surface. Water's boiling point depends on the surrounding pressure, at 1 atmosphere. Water boils at 100 degrees Celsius, but as pressure decreases, the boiling point drops. At the 0.006 atmosphere pressure found on Mars, water cannot exist as a stable liquid at any temperature. It sublimates directly from ice to vapor. If Earth's atmosphere were suddenly stripped of its nitrogen, the remaining pressure from oxygen and trace gases would be only about 0.22 atmospheres. At this pressure, water would boil at approximately 62 degrees Celsius, meaning that in many tropical and equatorial regions, surface water would begin to boil and evaporate. The hydrological cycle would be disrupted. Ocean surfaces would lose water at accelerated rates. The planet's climate would be thrown into chaos. Furthermore, lower atmospheric pressure reduces the efficiency of the greenhouse effect. Not because nitrogen itself is a greenhouse gas, it is not, but because pressure broadening is a critical factor in how greenhouse gases like CO2 and water vapor absorb infrared radiation. At higher atmospheric pressures, the absorption lines of greenhouse gases are broadened, meaning they can absorb radiation over a wider range of wavelengths, trapping more heat. Research published in the journal Nature has demonstrated that the atmospheric pressure of the early Earth, potentially influenced by higher or lower nitrogen levels, had a significant impact on surface temperatures. A 2012 study by Goldblatt and colleagues found that doubling the atmospheric pressure by adding Nitrogen could raise Earth's surface temperature by several degrees Celsius through enhanced pressure broadening of greenhouse gas absorption. Conversely, a lower pressure atmosphere would reduce the greenhouse effect and potentially plunge the planet into a frozen state. This means that nitrogen, while not a greenhouse gas itself, acts as a critical amplifier and regulator of the greenhouse effect, a thermostat knob that determines how effectively the actual greenhouse gases can do their job. Without sufficient nitrogen to maintain atmospheric pressure, Earth could freeze over entirely, even with the same concentration of CO2 and water vapor. The second critical function of nitrogen is its role as a diluent for oxygen. This may sound unglamorous, but it is literally a matter of life and death for every terrestrial organism. The current oxygen concentration of about 21% is a carefully balanced value with profound implications. Oxygen is essential for aerobic respiration, the metabolic process that powers virtually all complex life, but oxygen is also a powerful oxidizer, and at higher concentrations, it becomes genuinely dangerous. At oxygen concentrations above about 25%, organic materials become significantly more flammable. A world with 30 or 35% oxygen would be a world where forest fires burn hotter, spread faster, and occur more frequently. We have direct evidence of this from the geological record. During the late Carboniferous period, approximately 300 million years ago, atmospheric oxygen levels rose to an estimated 35%, the highest level in Earth's history. This period saw the evolution of truly giant insects, Meganeura, a dragonfly-like predator with a wingspan of up to 75 centimeters, or about 2.5 feet, and Arthropleura, a millipede-like arthropod that could reach lengths of over 2 meters, roughly 6.5 feet. These creatures could grow so large in part because the high oxygen atmosphere enhanced the efficiency of their tracheal breathing system, which relies on passive diffusion of oxygen through tiny tubes rather than active pumping by lungs. But the Carboniferous also saw widespread and devastating wildfires, as evidenced by abundant charcoal deposits in the fossil record. Forests burned regularly and intensely. If oxygen were to rise even further, say to 50 or 80%, the consequences would be apocalyptic. At 80% oxygen, virtually any organic material would be a fire hazard. A lightning strike in a forest would not just start a fire. It would create a conflagration of such intensity that it could sterilize the landscape. Wet vegetation would burn. Even materials that are effectively fireproof at today's oxygen levels would become combustible. Human civilization, which is built on the controlled use of fire, from cooking to metallurgy to internal combustion engines, would be essentially impossible. You could not light a candle without risking an uncontrollable blaze. You could not smelt iron or without triggering an explosion. The margin between useful fire and catastrophic fire would be vanishingly thin. Beyond fire risk, high oxygen concentrations are directly toxic to animals. Breathing pure oxygen at 1 atmosphere of pressure for extended periods causes a condition known as oxygen toxicity, which damages the lungs, causes seizures, and can be fatal. Premature infants exposed to high oxygen concentrations in incubators can develop retinopathy of prematurity, a condition that damages the retina and can cause blindness. Scuba divers breathing high oxygen mixtures at depth risk central nervous system oxygen toxicity, which can cause convulsions and drowning. The fact that our atmosphere contains only 21% oxygen is not an accident. It is a balance, maintained in part by the overwhelming presence of nitrogen as a diluent. Nitrogen does not react, does not burn, does not support combustion, and does not participate in oxidation reactions. It simply fills the atmospheric space that would otherwise be available to oxygen, keeping oxygen's partial pressure at a level that supports aerobic life without enabling the catastrophic flammability that would come with higher concentrations. In this sense, nitrogen is the fire extinguisher of the atmosphere, not by actively suppressing flames, but by passively diluting the gas that feeds them. The third major role of atmospheric nitrogen is providing climate stability through maintaining a consistent atmospheric mass. If the atmosphere were composed primarily of reactive gases like CO2 and oxygen, its total mass and pressure would fluctuate significantly as those gases were consumed and released by geological and biological processes. Volcanic eruptions would add CO2, increasing pressure and temperature. Periods of enhanced photosynthesis would remove CO2, reducing pressure and cooling the planet. The atmosphere would be a constantly shifting, unstable system, lurching between extremes. But because the atmosphere is 78% inert nitrogen, which does not participate significantly in short-term geological or biological cycles, the total atmospheric mass remains remarkably constant on human and even geological timescales. The nitrogen acts as ballast, a stable mass that anchors the atmosphere and prevents wild swings in pressure and temperature. This stability has been crucial for the evolution of complex life, which requires relatively consistent environmental conditions over millions of years. The evolution of large, complex organisms, fish, amphibians, reptiles, mammals, and eventually primates and humans, depended on a stable atmospheric environment that could support consistent ecosystems over geological time. Without nitrogen's stabilizing presence, Earth's atmosphere might have oscillated between dense, Venus-like states and thin, Mars-like states as CO2 levels waxed and waned, making the sustained evolution of complex life far less likely. Despite its inertness in the atmosphere, nitrogen is absolutely essential to life at the molecular level. And the inability of most organisms to use atmospheric N2 directly represents one of the most fascinating bottlenecks in all of biology. Every protein in every living cell contains nitrogen atoms. The amino acids that are the building blocks of proteins all contain at least one nitrogen atom, and many contain two or more. DNA and RNA, the molecules that carry genetic information and direct the synthesis of proteins, are built from nucleotide bases that are rich in nitrogen. Adenine, guanine, cytosine, thymine, and uracil all contain multiple nitrogen atoms. Chlorophyll, the pigment that makes photosynthesis possible, contains 4 nitrogen atoms at its core. ADP, adenosine triphosphate, the universal energy currency of cells, contains nitrogen. In short, nitrogen is woven into the very fabric of life. Without it, there are no proteins, no DNA, no RNA, no chlorophyll, no ADP, no life as we know it. And yet the vast reservoir of nitrogen in the atmosphere, approximately 3.9 quadrillion metric tons, of N2, is almost entirely inaccessible to the vast majority of living organisms. Plants cannot use it, animals cannot use it, fungi cannot use it. The nitrogen triple bond is simply too strong for any ordinary biological enzyme to break. This creates a paradox that has shaped the entire history of life on Earth. Organisms are surrounded by an atmosphere that is 78% nitrogen. They desperately need nitrogen to build their most essential molecules, and yet they cannot access it. It is like dying of thirst in the middle of the ocean. The resource is everywhere, but in a form that is unusable. The resolution of this paradox lies with a small, specialized group of microorganisms that evolved the remarkable ability to perform biological nitrogen fixation, the conversion of atmospheric N2 into ammonia, NH3, a form of nitrogen that can be incorporated into biological molecules. These nitrogen-fixing organisms, called diazotrophs, include certain species of bacteria and archaea. The most well-known are rhizobium bacteria, which form symbiotic relationships with leguminous plants such as soybeans, peanuts, clover, and alfalfa. In this symbiosis, the plant provides the bacteria with sugars and other carbon compounds as an energy source. And in return, the bacteria convert atmospheric N2 into ammonia, which the plant can use to synthesize amino acids and proteins. The bacteria reside in specialized root nodules, structures that maintain the low oxygen environment necessary for the nitrogen-fixing enzyme to function. Other important nitrogen fixers include free-living soil bacteria, such as Azotobacter and Clostridium, cyanobacteria such as Anabina and Nostoc that fix nitrogen in aquatic environments, and certain archaea found in extreme environments. The enzyme responsible for nitrogen fixation is nitrogenase, a complex metalloenzyme that contains iron and molybdenum at its active site. Nitrogenase catalyzes the reaction N2 plus 8H plus 8E plus 16 ADP 2 NH3 plus H2 plus 16 ADP plus 16 pi. a reaction that requires an enormous energy input of 16 ADP molecules per molecule of N2 fixed. This is one of the most energy-expensive biochemical reactions in nature, reflecting the tremendous difficulty of breaking the nitrogen triple bond. Nitrogenase is also extremely sensitive to oxygen, which irreversibly destroys the enzyme, which is why nitrogen-fixing organisms must either live in anaerobic environments or have evolved elaborate mechanisms to protect their nitrogenase from oxygen exposure. Global biological nitrogen fixation is estimated at approximately 100 to 140 teragrams of nitrogen per year on land, with marine nitrogen fixation adding roughly another 100 to 200 teragrams per year. These figures are approximate and continue to be refined by ongoing research, but the total biological fixation is on the order of 200 to 300 teragrams per year. The other natural mechanism for nitrogen fixation is lightning. When a lightning bolt strikes, it heats the air in its path to temperatures of roughly 30,000 Kelvin, about 5 times the temperature of the surface of the sun. At these extreme temperatures, the nitrogen triple bond can be broken thermally, and N2 and O2 in the air react to form nitrogen oxides, primarily nitric oxide. No, these nitrogen oxides are subsequently converted to nitrate, NO3-, in the atmosphere through reactions with water and oxygen, and the nitrate is washed to the ground by rain, where it becomes available to plants as a nitrogen source. Global nitrogen fixation by lightning is estimated at approximately 3 to 10 teragrams per year, a small fraction of biological fixation, but still a significant contribution, particularly in ecosystems where biological nitrogen fixers are scarce. Volcanic eruptions can also produce nitrogen oxides through similar high-temperature reactions, adding another small source of fixed nitrogen to the environment. Together, biological fixation and lightning-driven fixation are the natural mechanisms that bridge the gap between the enormous reservoir of atmospheric N2 and the biological demand for usable nitrogen compounds. The nitrogen cycle, which describes the movement of nitrogen through the atmosphere, biosphere, hydrosphere, and geosphere, is one of the most important biogeochemical cycles on Earth. Fixed nitrogen, in the form of ammonia, nitrate, nitrite, and organic nitrogen compounds, cycles through soils, water, plants, animals, and microorganisms in a complex web of transformations. Ammonification converts organic nitrogen from dead organisms back to ammonia. Nitrification, carried out by specialized bacteria such as Nitrosomonas and Nitrobacter, converts ammonia to nitrite and then to nitrate. Plants take up nitrate and ammonia through their roots and incorporate the nitrogen into amino acids and proteins. Animals obtain nitrogen by eating plants or other animals. And critically, denitrification, carried out by bacteria such as Pseudomonas, converts nitrate back to N2 gas, returning nitrogen to the atmosphere and completing the cycle. This return pathway is essential. Without denitrification, nitrogen would gradually accumulate in soils and oceans in fixed forms, depleting the atmospheric reservoir. The balance between nitrogen fixation and denitrification has maintained the atmospheric nitrogen concentration at approximately 78% for hundreds of millions, possibly billions of years. This is a dynamic equilibrium, not a static state. Nitrogen is constantly being removed from the atmosphere by fixation and returned by denitrification. But the two processes approximately balance over long timescales, keeping the atmospheric concentration stable. It is one of the most remarkable examples of planetary homeostasis in all of Earth science. Now consider what would happen if the atmospheric balance were different, if nitrogen's proportion were significantly higher or lower, or if oxygen dominated instead. These thought experiments are not merely academic. They illuminate just how finely tuned the current atmospheric composition is for the flourishing of life and civilization. Imagine first a world where nitrogen constitutes only about 40% of the atmosphere, with the total atmospheric pressure dropping accordingly to perhaps 0.6 or 0.7 atmospheres. In such a world, the reduced atmospheric pressure would lower the boiling point of water, making it less stable as a liquid, particularly in warmer regions and at higher elevations. The reduced pressure broadening would weaken the greenhouse effect, potentially cooling the planet significantly. High-altitude regions, which already have thin air, would become essentially uninhabitable for oxygen-breathing animals. The reduced atmospheric density would also diminish the atmosphere's ability to block ultraviolet radiation and cosmic rays, increasing the radiation dose at the surface and elevating the risk of cancer and genetic mutations for terrestrial organisms. With less atmospheric mass, weather patterns would change. Winds could be weaker in some respects due to the lower density, but temperature differentials between day and night and between equator and poles could be more extreme, leading to violent storms. Agriculture would be more challenging, as the lower pressure would affect the rates of gas exchange in plant leaves, and the higher relative proportion of oxygen would increase fire risk. This low-nitrogen Earth would be a harsher, less stable, less hospitable world. Now imagine the opposite. A world with 90 or 95% nitrogen and a total atmospheric pressure of perhaps 1.5 to 2 atmospheres. In this dense nitrogen world, the higher atmospheric pressure would amplify the greenhouse effect through enhanced pressure broadening, potentially warming the planet by several degrees Celsius, even without any increase in greenhouse gas concentrations. The denser atmosphere would affect acoustics. Sound would travel differently, potentially farther and at different speeds. The sky might appear a deeper shade of blue due to enhanced Rayleigh scattering. Birds and flying insects would find it easier to generate lift in the denser air, potentially enabling the evolution of larger flying organisms. For humans or human-like organisms that evolved in such conditions, the slightly elevated nitrogen partial pressure could cause mild nitrogen narcosis-like effects, similar to what deep-sea divers experience at depth. Though evolutionary adaptation might mitigate this, the denser atmosphere would provide better protection against meteors, cosmic rays, and ultraviolet radiation. But the elevated temperatures from the enhanced greenhouse effect could push tropical regions toward uninhabitable heat, and the stronger greenhouse warming could destabilize ice caps and raise sea levels. The overall effect would be a warmer, denser, and in many ways more dynamic world, with both advantages and dangers. Finally, consider the most extreme scenario: an atmosphere with 80% oxygen and only 20% nitrogen, essentially a reversal of the current proportions. This oxygen-rich world would be lethally dangerous. At 80% oxygen, at 1 atmosphere of total pressure, the partial pressure of oxygen would be approximately 0.8 atmospheres, nearly 4 times the current level. This is well above the threshold for oxygen toxicity in humans. Breathing this air for even a few hours would cause pulmonary edema, seizures, and death. Even organisms adapted to higher oxygen levels would face enormous challenges from oxidative stress, the chemical damage caused by reactive oxygen species to DNA, proteins, and cell membranes. The world itself would be a tinderbox. The auto-ignition temperature of many organic materials drops significantly at elevated oxygen concentrations. Forests, grasslands, and any ecosystem with dry organic matter would be subject to frequent, catastrophic wildfires. A single lightning strike could ignite a firestorm covering hundreds of square miles. Human civilization, as we know it, could not exist in such a world. Metallurgy, which requires controlled combustion, would be impossible to practice safely. Cooking over an open flame would be suicidal. Internal combustion engines, which rely on controlled detonation of fuel-air mixtures, would be uncontrollable. The entire trajectory of technological civilization, which depended on mastering fire, would be aborted. An 80% oxygen world might support certain forms of life, possibly very small organisms with extremely efficient antioxidant systems, but it would not support complex ecosystems, large animals, or technological civilizations. The current 21% oxygen concentration is not arbitrary. It sits in a narrow window that is high enough to support vigorous aerobic metabolism, but low enough to prevent the atmosphere from becoming a perpetual combustion hazard. And it is nitrogen, the 78% majority, that maintains this window by occupying the atmospheric space that would otherwise be available to oxygen. The relationship between nitrogen and human civilization reached a critical inflection point at the beginning of the 20th century, when 2 scientists working in the United States, Fritz Haber and Carl Bosch, developed the Haber-Bosch process. a method for synthesizing ammonia from atmospheric nitrogen and hydrogen gas using high temperature, high pressure, and an iron-based catalyst. The reaction is deceptively simple, N2 plus 3H22 and H3. But making it work on an industrial scale required pressures of 150 to 300 atmospheres and temperatures of 400 to 500 degrees Celsius. Conditions that pushed the boundaries of early 20th century engineering. Haber demonstrated the feasibility of the reaction in 1909, and Bosch, working for the chemical company BASF, scaled it up to industrial production by 1913. The impact of the Haber-Bosch process on human history is almost impossible to overstate. Before its invention, the amount of food the world could produce was fundamentally limited by the availability of nitrogen fertilizer. Farmers relied on crop rotation with nitrogen-fixing legumes, animal manure, and mined deposits of sodium nitrate from places like the deserts of South America to maintain soil fertility. These sources were insufficient to feed a rapidly growing global population. Famines were common and frequently catastrophic. The Haber-Bosch process broke through this limitation by providing an essentially unlimited source of nitrogen fertilizer, manufactured directly from the air. The consequences were immediate and dramatic. Global food production surged. Crop yields per acre doubled and tripled. The world population, which had been approximately 1.6 billion in 1900, exploded to over 8 billion by the early 2020s, a five-fold increase in little more than a century. A 2008 study published in Nature Geoscience estimated that without the Haber-Bosch process, approximately half of the world's current population could not be fed. The nitrogen atoms in our bodies tell this story directly. Studies have estimated that roughly 50% of the nitrogen atoms in the average human body today were fixed by the Haber-Bosch process, meaning they were pulled from the atmosphere in an industrial facility and incorporated into fertilizer, then into crops, and finally into the proteins and DNA of our cells. We are, in a very literal sense, half made of industrially fixed air. But this triumph of chemistry came with a dark side that is still unfolding. The Haber-Bosch process currently fixes approximately 150 teragrams of nitrogen per year, which is comparable to or greater than the total amount fixed by all natural biological processes on land combined. Humanity has effectively doubled the rate at which nitrogen enters the biosphere, with profound environmental consequences. Much of the nitrogen applied as fertilizer is not taken up by crops. Estimates suggest that only about 50% of applied nitrogen is actually absorbed by plants, with the rest leaching into groundwater, running off into rivers and streams, or volatilizing into the atmosphere. This excess reactive nitrogen cascades through ecosystems, causing a chain of problems known as the nitrogen cascade. In aquatic systems, nitrogen runoff causes eutrophication, the excessive growth of algae and aquatic plants, which, when they die and decompose, consume oxygen and create hypoxic dead zones where fish and other marine life cannot survive. The Gulf of Mexico dead zone, fueled primarily by nitrogen and phosphorus runoff from agricultural land across the central part of the United States, has in recent years covered an area of roughly 6,000 to 7,000 square miles during summer months, an area about the size of New Jersey. Similar dead zones have been documented in over 500 locations worldwide, including the Chesapeake Bay, the Baltic Sea, and coastal areas throughout East and South Asia. In the atmosphere, excess nitrogen contributes to air pollution in the form of nitrogen oxides, NOx, which are precursors to smog and ground-level ozone. Nitrous oxide, N2O, a potent greenhouse gas with approximately 273 times the warming potential of CO2 over a 100-year period, is released from agricultural soils and is also a significant driver of stratospheric ozone depletion. Nitrogen deposition from atmospheric pollution alters the composition of natural ecosystems, favoring nitrogen-loving species and reducing biodiversity. The paradox is striking. Nitrogen, the inert gas that shaped the atmosphere through its refusal to react, has become one of the most disruptive pollutants on the planet when converted to reactive forms and released in excess by human activity. The challenge of the 21st century is to feed a growing population without drowning. ecosystems and reactive nitrogen to find a sustainable balance that mimics the natural nitrogen. Cycle's elegant equilibrium. Looking further ahead, nitrogen presents one of the most formidable challenges for humanity's expansion beyond Earth. When we imagine future settlements on the Moon or Mars, the conversation naturally focuses on water and oxygen, how to find water ice, how to electrolyze it into oxygen for breathing and hydrogen for fuel. But a breathable atmosphere requires more than just oxygen. A habitat filled with pure oxygen at a livable pressure would present the same catastrophic flammability risks described earlier, and at reduced pressures, as was used in early American space missions like Mercury, Gemini, and Apollo, which used pure oxygen at about 1/3 of an atmosphere. The fire risk is still elevated, as tragically demonstrated by the Apollo 1 fire in January 1967, which killed astronauts Gus Grissom, Ed White, and Roger Chaffee when a spark ignited the pure oxygen atmosphere of their command module during a ground test. Modern spacecraft and the International Space Station use a mixed nitrogen-oxygen atmosphere at approximately sea level pressure, mimicking Earth's atmospheric composition with roughly 79% nitrogen and 21% oxygen. But maintaining this nitrogen supply in space is a logistical challenge. The ISS receives nitrogen resupply from Earth in pressurized tanks delivered by cargo vehicles. For a short-duration mission in low Earth orbit, this is manageable. But for a permanent settlement on the Moon or Mars, importing nitrogen from Earth would be prohibitively expensive. Launching mass from Earth's surface to orbit costs thousands of dollars per kilogram, and the quantities of nitrogen needed for a large habitat would be enormous. A sealed habitat for even a few hundred people, with agricultural greenhouses for food production, would require millions of kilograms of nitrogen gas to maintain a breathable atmosphere, plus additional nitrogen in the form of fertilizer for crop growth. Mars has some nitrogen in its atmosphere, about 2.7% of a very thin atmosphere, but extracting it would require processing vast volumes of Martian air. The total atmospheric mass of Mars is estimated at about 25 trillion kilograms, of which roughly 675 billion kilograms is nitrogen. While this sounds like a lot, it is spread across the entire surface area of a planet, at extremely low pressure, and concentrating it into usable quantities would be an enormous engineering challenge. The Moon has essentially no atmosphere, and thus no nitrogen source at all, though there may be trace amounts of nitrogen-containing compounds in permanently shadowed craters near the poles, delivered by comet and asteroid impacts over billions of years. For any serious off-Earth settlement, nitrogen will be one of the most precious and limiting resources. The engineering challenges of establishing a closed-loop nitrogen cycle, where nitrogen is recycled through crops, human waste, and atmospheric processing with minimal losses, will be as important as any other aspect of life support system design. In a very real sense, the availability of nitrogen will determine the size, sustainability, and ultimate viability of human settlements beyond Earth. Some visionary scientists and engineers have considered even more ambitious scenarios, such as terraforming Mars, gradually transforming the Martian environment to make it habitable for humans without spacesuits. Any realistic terraforming plan would need to address the nitrogen deficit. Even if we could thicken Mars's atmosphere by releasing CO2 from polar ice caps and carbonate rocks through orbital mirrors, nuclear heating, or other methods, the resulting atmosphere would still be overwhelmingly CO2, which is toxic to humans at high concentrations and would provide no nitrogen for plant growth or ecosystem development. Importing nitrogen from other sources in the solar system has been proposed. For example, redirecting nitrogen-rich comets, or mining the nitrogen ice on Triton, Neptune's largest moon, but these are feats of engineering so far beyond current capabilities that they remain firmly in the realm of speculation. The fundamental lesson is clear. Nitrogen is not just a background gas on Earth. It is the invisible infrastructure upon which our entire biosphere is built, and any attempt to create a new biosphere elsewhere must reckon with the nitrogen challenge from the very beginning. Mastering nitrogen, learning to fix it, cycle it, conserve it, and deploy it efficiently in closed systems may well be the defining technological challenge of humanity's future as a spacefaring civilization. The story of nitrogen is ultimately a story about hidden importance, about the power of what seems passive and unremarkable. We celebrate oxygen because we feel its absence in seconds. We worry about carbon dioxide because we can measure its impact on climate. We track water because we can see and feel it. But nitrogen, the invisible majority, escapes our notice entirely. It does not smell, it does not taste, it does not react, it does not warm or cool. It does not nourish or poison. It simply is. And yet, if it were not there, if those 4 out of every 5 molecules in every breath were missing, our oceans would evaporate. Our forests would burn, our climate would lurch between extremes, and life as we know it would be impossible. The kingdom of the atmosphere belongs to nitrogen not because nitrogen seized power, but because it endured while all others fell away. It is the element that won by patience, by stability, by the simple virtue of persisting when everything around it was transformed, dissolved, consumed, or lost. In a universe where hydrogen and helium reign supreme, on a planet where carbon dioxide once smothered the sky, in an atmosphere where oxygen gets all the glory, nitrogen is the quiet constant, the invisible sovereign, the foundation on which everything rests. The next time you step outside and draw a breath, remember that 4/5 of what enters your lungs is this ancient, unassuming gas, a molecule forged in the furnaces of long-dead stars, released from the volcanoes of a young and violent Earth, preserved across 4.5 billion years of planetary evolution by its own supreme indifference to the chemical chaos around it, and now silently sustaining the only known world in the universe where beings can look up at the sky and wonder why the air is what it is.